Hello everyone, my name is Junyi Han and I'm a year 2 PhD student at the University of Sheffield, and I'm happy to show our work from our group titled as a Thermo-Responsive shape-changing Milli-Robot. While talking about shape-changing, so one of the methods is folding. So there are lots of foldable structures that become very popular to be used in mini and micro robots. And also to achieve this goal without embedding any electrical components into this folding mechanism, well, one approach is to use a smart material. This kind of material is known for its ability to respond to physical stimuli, for example, the pH, the light, or the temperature. Well, in those cases, the materials can change their own physical properties to activate the folding mechanism as the response to the physical stimuli from the environment. So in our study, we used the temperature as the main parameter from the environment. And we designed and implemented a self-foldable string robot, like here shown in the figure, with a temperature-driven volume-changing hydrogel PNAPAM. We make two PNAPAM beams as the active layer, which can change its own physical property. And we use a 20 micron thick PVC string as the passive layer to connect these two PNAPAM beam together with a magnet. So for each PNAPAM beam, it has 1 millimeter in height and 12 millimeter in length. And in total, the robot has a 30 millimeter in length. So the hydrogel PNAPAM can change its hydrophilicity between 22 to 45 degrees. At a lower temperature, it absorbs water and swells. And since the passive layer under it is flexible and doesn't swell, so the string can fold around 90 degrees each side. However, at a higher temperature, the hydrogel shrinks and make the string flat. So here, the animation on the right showing the shape changing process when the temperature is changing between 22 and 45 degrees. Well, to fabricate the robot, we are using the same technique with my colleague's previous publication. So we first prepare the PNAPAM solution by mix 3 reagents, monomer napalm, cross-linker, and photoinitiator with a ratio at 200 to 8 to 4. And for the mixture is diluted with a 1 milliliter solution of distilled water and ethanol with 50 to 50 ratio for every 200 milligram of napalm. So after that, we fix the string on a 3D printed aligner and activate the string's surface in air plasma. Then fill the silicon mold with PNAPAM solution and place a magnet in the middle with some UV adhesive on the top. Then gently cover the string on the top and then expose to UV light at 20 watts per centimeter square for 2 minutes to cure both the PNAPAM and the UV adhesive. And finally, lift them up and cut the rest part of the string. Then the robot is ready. In the experiment, the robot is placed in a water tank filled with deionized water, and we used a coil system to generate a magnetic field to control the robot, because there is a magnet on it. And the robot can perform a rolling motion controlled by the magnetic field and at strings around 1 milli-Tesla, and the robot can roll at around 63 rounds per minute. Well, this video showing how it works at 45 degree. We can see the two arms of the robot are flat at 45 degree, and while it's rolling, these two arms swings a little bit because it's flexible and the density is similar to water. But these two arms doesn't get involved to the rolling motion. However, at room temperature, as the water cools to 22 degrees, and the arms bend over and increase the cross-section area of the robot contact with the surface. So the robot can roll faster, but due to the flexible arm and unbalanced weight, it cannot roll as a fully rigid body. So compare these two rolling motion, these two videos. The linear speed was obviously increased, but only when the arms are contact with the surface as a support of the robot. Here in this plot is showing the distance, the movement distance versus the time. You can see there is a short increase in the blue line. So this blue line should be 22 degrees. So on average, the linear rolling speed is increased by 50% from 13 to 20 millimeters per second. And also the maximum height is around 3 times higher than it at when the arms are flat. So this difference also gives the ability to climb up some obstacles. In this video, we put some obstacles with 5 millimeter height, and we can see at room temperature at 22 degrees, the robot can climb up and push the object on the upper level, but it cannot climb up to the first step at 45 degrees. So in addition, we add a Hall effector sensor area between the water tank and the coil system. And this sensor area is used to localize the robot and also navigate the robot to move from a random position to towards the destination. So here I mark the random start point. Here is a green dot, and the destination is a red dot. And also I mark the ideal trajectory in the yellow dash line and the real trajectory in the blue line. So while it's rolling inside the workspace, and it generates arrows due to the unbalanced deformation each arm and skips while rolling. So at last, it arrives at the destination and slightly adjust the position by rolling further away and then rolling back. Well, in conclusion, we have developed this shape-changing string robot, which can float by changing the temperature as a physical stimuli, and it is controlled by the external magnetic field generated by the coil system. And the shape changing can increase the linear rolling speed and also allow the robot to overcome some obstacles. And finally, with the help of the sensor array, the robot can be navigated within the workspace and moving towards the destination from a random position. And the future work will be further minimize the robot and also apply some more functionality to by developing the design of the robot. And finally, following with some references I have used in my slides. And finally, I'd like to thank all the members from our group, and also thanks to our supervisor, Dr. Shoki Miyashita. And also, thank you for all your attentions, and I'm happy to answer any questions from you.